What specific problem does your method or algorithm aim to solve, particularly in the context of understanding and interpreting vision transformers like CLIP?
Our method aims to address the limited understanding and interpretability of vision transformers, specifically CLIP, by applying sparse autoencoders, SAEs, to analyze and manipulate the internal representations of the model. We focus on revealing fundamental differences in how vision and language processing mechanisms operate within CLIP, particularly through the lens of feature sparsity and steerability. By training SAEs on CLIP's vision encoder, we uncovered distinct activation patterns and the steerability of features, which allows us to improve model performance on challenging tasks such as disentanglement and defense against typographic attacks. Our findings not only enhance theoretical insights into CLIP's internal workings, but also provide practical tools for controlling and optimizing model behavior, thereby contributing to the safety and reliability of multimodal systems. Ultimately, our work establishes a foundation for more systematic approaches to understanding and interpreting vision transformers.
How does the proposed method using sparse autoencoders, SAEs, work? Illustrate the process step by step, specifically how the SAEs are trained and applied to the CLIP vision encoder.
The proposed method using sparse autoencoders, SAEs, involves several key steps in training and application to the CLIP vision encoder. First, two variants of SAEs are trained on the activations from the residual stream of each layer of the CLIP VIT model, with one using ReLU activation, vanilla SAEs, and the other using a TopK activation function, TopK SAEs. The training is conducted in both general and task-specific settings, where general-purpose SAEs are trained on ImageNet 1K to capture a wide range of features, while task-specific SAEs focus on datasets like Celeba and Waterbirds to learn features relevant to specific tasks. Once trained, the SAEs are utilized to analyze and manipulate the model's internal representations. The analysis reveals the sparsity of features, with a steerability metric introduced to quantify how effectively specific SAE features can influence model outputs. By selectively suppressing or amplifying these features, the SAEs improve performance on various vision disentanglement tasks, such as attribute separation in Celeba and background suppression in Waterbirds. This process not only enhances the interpretability of the CLIP vision encoder, but also provides practical tools for improving model behavior against typographic attacks, achieving state-of-the-art performance in robustness.
Can you provide a simple yet illustrative example that demonstrates how the steering of features through SAEs impacts the model's output? Walk through the main steps of the algorithm using a specific example from your experiments.
In our experiments, we demonstrated the impact of steering features through sparse autoencoders, SAEs, on the model's output using a specific example involving the feature dragon. To illustrate this, we first obtained the image embedding for a given input image using CLIP's vision encoder. Next, we selected the dragon feature and manipulated its activation across all patches by applying a steering strength, which allowed us to observe changes in the model's output probability distribution. By amplifying the dragon feature to its maximum strength, we found that it concentrated the probability mass towards the concept of dragon, effectively steering the model's prediction towards this specific class. This process exemplifies how feature steering can provide precise control over the model's outputs, as we quantified the changes in the output distribution before and after the feature manipulation, showcasing the effectiveness of our SAE-based approach in influencing model behavior.
What theoretical or practical benefits does your method offer compared to existing approaches in interpreting vision transformers? Can you highlight areas of improvement in accuracy, interpretability, or efficiency?
Our method offers significant theoretical and practical benefits over existing approaches in interpreting vision transformers, particularly through the use of sparse autoencoders, SAEs. Theoretically, we provide a systematic and quantitative analysis of steerability in CLIP's features, revealing that approximately 10 to 15% of features are steerable, which allows for more precise manipulation of model outputs compared to traditional neuron-level steering. Practically, our approach improves accuracy in challenging vision disentanglement tasks, such as achieving state-of-the-art performance against typographic attacks and enhancing performance on datasets like Celeba and Waterbirds by effectively suppressing spurious correlations. Additionally, our method enhances interpretability by identifying interpretable monosemantic directions in the latent space, which contrasts with the polysemantic nature of individual neurons in existing models. Overall, our work establishes a foundation for better understanding and controlling vision transformers, leading to improved model behavior and reliability in safety-critical applications.
How did you validate or test the effectiveness of your method? Describe the experimental design, datasets used, performance metrics, and how you demonstrated the advantages of your approach.
To validate the effectiveness of our method, we conducted experiments using 3 distinct datasets: Celeba, Waterbirds, and ImageNet 100, focusing on tasks such as attribute separation, background suppression, and defense against typographic attacks. For each dataset, we identified say features aligned with spurious correlations and typographic knowledge, employing a systematic approach to select features based on their activation differences across subsets of data. Performance metrics included overall accuracy and worst group accuracy, with specific thresholds set to balance model performance and fairness. Our results demonstrated that targeted feature suppression with SAEs consistently improved disentanglement across all layers for Celeba and many layers for Waterbirds, with notable accuracy improvements in worst group performance. Additionally, our method outperformed state-of-the-art techniques in defending against typographic attacks, showcasing the practical utility and advantages of our say-based approach in enhancing model robustness and interpretability.
What specific results were achieved with your method in terms of performance on the vision disentanglement tasks and robustness against typographic attacks? How do these results compare to state-of-the-art performance?
Our method demonstrated significant improvements in performance on vision disentanglement tasks, specifically achieving a worst group accuracy increase from 78% to 81.11% for the Celeba dataset and from 43% to 24.61% for the Waterbirds dataset. The optimal layers for disentanglement were identified as layers 7 and 8 for Celeba and layer 2 for Waterbirds, with the best overall accuracy reaching 67% for Celeba and 36.6% for Waterbirds under relaxed conditions. In terms of robustness against typographic attacks, our approach outperformed the current state-of-the-art methods, particularly on the Paint dataset, while remaining competitive with defense prefix methods on other datasets. This indicates that our say feature steering not only enhances disentanglement, but also fortifies the model against adversarial typographic manipulations, establishing a new benchmark in both areas.